In our previous video, we have calculated the equivalent capacitance of four parallel plate conductors, in which the second and third plates were connected with a battery, and first and fourth were connected with an electric conductor. Now, it is slightly different from my previous question. In this case, first and third, these two are connected with each other by a conductor, and second and fourth plate are connected with a battery terminal. So we have to calculate the equivalent capacitance of this system. So in order to solve this, let us consider this system a four parallel plate capacitor or a four parallel plate conductor. This is our second plate, this is our third plate, and this is our fourth plate. Now this first and third plate are connected by an electric conductor. So 1 and 3 constitute an isolated system of conductor. So total charge of this system remains constant. Since initially Q1 was 0 and Q3 was also 0, so their sum is also 0. So we can say that Q1 plus Q3 equals to 0. Now this second plate is connected to a battery, positive terminal of a battery, so it will have a charge of plus Q. And the fourth plate, which is connected to negative terminal of a battery, so it will have a charge of minus Q. So we can say that Q2 equals to Q and Q4 equals to minus Q. Now in my previous calculation, I have shown that the total charge appearing on F1L, that is on extreme left, on its left face is Qt, and it is equal to total charge appearing on the extreme right on its right side, that is also Qt. This I have explained in my previous videos where I have explained my theories. So if you are interested, you can see the link is given in the description below. So Qt we have calculated as 0. So these are the charges which are appearing on F1L and F4R. Once Qt is known, suppose we assume that the charge appearing on F1R is Q. So by Gauss law, F2L will be minus Q. This is based on Gauss law. And since total charge on the second capacitor or second conductor has to be Q, so charge appearing on F2R should be capital Q plus small q. This is the charge which is appearing on second F2R. And by Gauss law, the charge appearing on F3L will be minus times of this Q plus capital Q plus small q, which is minus times of Q capital Q minus small q. So this is our charge which is appearing on third plate, that is on F3L. Now total charge on this fourth plate has to be 0, and we have calculated that F4R is 0, so F4L has to be minus Q. And from Gauss law, F3R will have minus times of minus Q, that is plus Q. So now this charge distribution we have done, and here this once this small q, the value of small q in terms of capital Q is known, part of our question or part of our problem is solved. So in order to determine the relation between capital Q and small q, we have to observe two things, that first and this third plate are connected with a conducting wire, so potential difference between 1 and 3 should be 0. This, and second is to calculate the potential difference between 1 and 3, or we can say that 1 2 2 3 and 3 4. So potential difference between 1 and 2, that is V1 minus V2, is proportional to this charge Q. What I am saying is that if we consider the space 1 and 2, then the charge appearing to the left of this space, that is on face F1R, and the charge is appearing on F1R is small q. So potential difference will be proportional to this small q. So V1 minus V2 is Q divided by epsilon naught A into T. Similarly, between, if we are considering potential difference between 2 and 3, that is V2 minus V3. So this is our space, and this is the face which is left of this space, which is F2R, and this is the charge capital Q plus small q, which is appearing on F2R. So V2 minus V3 is capital Q plus small q divided by epsilon naught into A into D. So now we have calculated V2 minus V3. So in order to calculate V1 minus V3, if we simply add these two, we will get the value of V1 minus V3. Although this is not required, yet I have calculated, that is V3 minus, sorry, it is required for calculation. So V3 minus V4 is, we are considering this space. So to the left of this space is the face F3R, and the charge appearing on this face is capital Q. So V3 minus V4 is capital Q divided by epsilon naught A into T. So now we have calculated V1 minus V2, V2 minus V3, V3 minus V4. In order to calculate V1 minus V3, which that is the first and the third plate which were connected by an electric conductor. So V1 equals to V3, or you can say that V1 minus V3 is 0. So if we add these two, we will get the relation of V1 minus V3, and that equals to Q plus capital Q plus small 2q divided by epsilon naught A into D, and this will be 0. So we can obtain capital Q plus 2q equals to 0, or q equals to minus q by 2. Once this small q is known, everything is almost known in terms of capital Q. We can write small capital Q plus small q, and if we substitute the value of small q, you will get small q by 2. Now this value we have calculated. This is qt, and that is 0. And similarly, this value is also qt, and it is 0. And small q we have calculated. Small q is minus q by 2. So once this is known from Gauss law, charge on F2L will be capital Q by 2. This we can calculate. Similarly, since total charge remains Q, so this value, that is charge appearing on F1R, has to be Q by 2. And from Gauss law, charge on F3L should be minus Q by 2. Now this value on fourth plate on its left side, this should be minus q, so that total charge remains minus q because F4R is 0. And from Gauss law, charge on F3R should be capital Q. Now the potential difference between 2 and 3, potential difference between 2 and 4, it is connected by a battery. So V2 minus V4 is the potential difference phi, and V2 minus V4 we have calculated previously. When we add V2 minus V3 and V3 minus V4, we will get V2 minus V4, and that equals to 3q divided by 2 epsilon naught S into D. So if we substitute q by phi, we will get q by phi as 2 epsilon naught S by D, and this is the definition of capacitance. So C equals to q by phi, and that equals to 2 epsilon naught S divided by 3D. This is the required capacitance which was asked in our question. Thank you.